Ever wondered how scientists design new materials for everything from smartphone screens to biodegradable plastics? It all starts with understanding polymers, those incredible long-chain molecules that make up everything from your water bottle to your favorite t-shirt. But here's the tricky part. Predicting their properties is like trying to guess a recipe just by tasting the final dish. Traditional methods focus on individual building blocks, called monomers, but they miss the big picture. See, when monomers link together during polymerization, the resulting material's properties, like strength, flexibility, or conductivity, can be totally different from the original pieces. That's where this new research comes in. A team from Tsinghua University has developed a groundbreaking framework called MIPS, short for Multimodal Infinite Polymer Sequence Pre-Training. So how does MIPS work? Instead of treating polymers as simple collections of monomers, it models them as infinite sequences, like an endless chain of building blocks. But here's the clever part. It doesn't just look at the order of the monomers. It also captures two critical dimensions: the topology, how the monomers are connected, and the spatial arrangement, their 3D shapes. Think of it as analyzing both the blueprint of a building and the actual 3D structure of its rooms. The researchers tackled a big challenge: how to represent these infinite sequences effectively. They introduced a technique called star linking, which connects monomers in a way that preserves their relationships during polymerization. But wait, there's a catch. Some polymer structures, like those with ring-shaped side chains, can fool traditional methods. To fix this, they developed backbone embedding, a way to give the model a better memory of the polymer's core structure. The results? MIPS outperformed existing methods across 8 different polymer property prediction tasks. It's like giving scientists a supercharged tool to design materials faster and more accurately. And the best part? The framework's ability to handle both topological and spatial data opens the door to discovering polymers with entirely new properties. Think self-healing materials or ultra-efficient solar cells. So what's next? This research isn't just about better predictions. It's about unlocking the full potential of polymer science. By bridging the gap between molecular structure and real-world applications, frameworks like MIPS could revolutionize everything from medicine to sustainable technology. But this isn't the only breakthrough in AI-driven materials science. Imagine a molecule as a complex puzzle. Some pieces, they're game changers. In a recent study, researchers trained an AI model to predict properties like bandgap, essentially, how easily a material conducts electricity. But here's the twist: they didn't just guess. They mapped which molecular fragments were key. Think of it like baking a cake. If you swap flour for sugar, the result changes. The AI learned which ingredients, like long carbon chains or sulfur rings, make the difference. Take the egg dataset, a collection of molecular structures. The AI discovered that fragments like COC, a carbon-oxygen-carbon chain, or CCCCC, a long carbon chain, boosted predictions. Why? These structures probably create stable, predictable patterns. But then there's C1CCSC1, a sulfur-containing ring. It had the opposite effect, like adding a surprise ingredient that throws the recipe off. The model learned that some parts help, others hinder, just by analyzing millions of examples. But how did it figure this out? The team used a technique called fragment analysis. They broke molecules into smaller pieces, tested each one's impact, and saw which parts the AI relied on. It's like asking, does the sugar in this cake make it sweeter, or is it the vanilla? The answer. Some fragments are crucial, others are red herrings. Why does this matter? Imagine designing a solar panel material. The AI could highlight which molecular structures maximize efficiency, skipping the guesswork. Or developing a new drug, it might flag which chemical groups are vital for effectiveness. This isn't just about speed. It's about understanding chemistry at a deeper level, uncovering secrets hidden in the molecular code. So next time you see a material or medication, remember, behind the scenes, AI is decoding the molecular recipe, one fragment at a time. Thanks for watching. If you want to see how AI is rewriting the rules of science, hit subscribe. And drop a comment. What molecule would you want an AI to decode?